Right. Hello, everyone, and thank you for coming to week 5 of the SPAAM seminar series. We're going to start with our first speaker, which is Kairan from the Department of Computer Science, and she's going to talk to us about what makes unlearning hard and what to do about it.
So, hello, everyone. My name is Kairan. I'm a computer science PhD student at Warwick. I'm very happy to be here to share our recent work on machine unlearning, which just got accepted to units last year. The paper is titled "What Makes Unlearning Hard and What to Do About It," where we explore the interpretable factors that affects the difficulty of an unlearning problem and how we can leverage these insights to improve unlearning. So before moving on to our findings, let's start with a brief introduction of machine unlearning. So machine unlearning essentially is to remove the effect of a subset of training data from a pre-trained model so that the model's output will no longer reflect that information. It's very important for example, protecting users' privacy or improving models' performance by removing biases or improving fairness, so on and so forth. So here is a simple use case to give you an idea about how unlearning works in image classification task. So we initially train a model using a lot of pictures from different people. And the model is trained to classify these pictures. And here in unlearning, we call it original model. And now we receive this request from one of the user. He said, okay, I don't want my pictures to get involved anymore, so please delete my pictures from the model. His pictures is called the forget set in unlearning. So obviously we want the model to forget this part of knowledge. So the most straightforward way is to retrain this model from scratch without this guy's pictures. And in unlearning, we call it retrained model. So since the model have never seen this guy's pictures during training, which is exactly what we want for unlearning. So here we consider this retrained model as the gold standard in unlearning. However, we all know retraining a model is very expensive in practice. So we find an alternative way to do this. We apply an unlearning algorithm on this pre-trained model to trick the model a little bit so that the model can forget this part of knowledge. And we get the unlearned model this way. And to measure how successful this unlearning process is, we compare these two models and to see how close they are. And ideally, we want this unlearned model to match as closely as possible to this gold standard. So now let's formally define this problem. We have an original model trained on the entire data set. And then we divide this entire data set into two parts. One is called forget set, which we want the model to forget this part of knowledge. And the remaining data, we call it retain set in unlearning, which means we want the model to retain the knowledge of the remaining data. And we then apply an unlearning algorithm on this original model to get an unlearned model. And to evaluate this process, we use retrained model. And if these two models are epsilon delta close, then we said this unlearning algorithm U has achieved epsilon delta unlearning. So when epsilon and delta are equal to 0, which means we have achieved exact unlearning, which means we have completely removed the influence of the forget set. And this is typically achieved by retraining from scratch. And when epsilon and delta are greater than 0, we call it approximate unlearning. which means we have successfully reduced the influence of the forget set without full retraining. So when it comes to the evaluation of unlearning, as mentioned earlier, of course, we want the model to successfully forget, right? But at the same time, we want the model to retain good utility as well. And a commonly used way to measure this is to use accuracy. So here we use the accuracy on the forget set to measure the forgetting quality. And we use the accuracy on the retain set and the holdout test set to measure model utility. So which means we want the model to still work well on the remaining data. And at the same time, we want the model to still be able to generalize well on the holdout test set. So we want the model to do well in both sides, and to capture this balancing act, we propose this tug-of-war metric, which is calculated in this formula. So we can see that it has 3 terms, and for each term, we calculate the accuracy difference between the unlearned model and the gold standard retrained model. And we calculate this difference on the forget set, retain set, and test set. And we reward the model that achieves a similar performance, similar accuracy to the retrained model. So this metric scales from 0 to 1, and higher means better unlearning. So now let's go back to this work. Why do we want to understand what makes unlearning hard? So it can help us to decide which unlearning method to use when we are given a unlearning request. It also reveals cases when retraining from scratch is necessary because all the other methods are not enough. And it also opens up ways to improve unlearning algorithms and evaluation protocols. So this leads us to ask, are there interpretable factors that affect unlearning difficulty? And if so, how do they impact different sort algorithms? So the first factor we found is the entanglement between the forget set and the retain set in the embedding space. And based on previous work, we use this entanglement score to measure this entanglement. So this is the formula to calculate this entanglement score. It's calculated between 2 sets, and a higher entanglement score means these 2 sets are more entangled in the embedding space. So now we want to study how this entanglement impacts unlearning difficulty. So we create 3 different settings with different forget retain partitions with low entanglement, medium entanglement, and high entanglement respectively. So we can see from these visualizations in each plot, the yellow dots are the forget set examples, and the blue dots are the retain set examples. And we see they indeed have different level of entanglement. And then we have these 3 different settings. We test a bunch of different unlearning baseline algorithms across these 3 settings and compare their performance. So here is the results. We see in x-axis, we have a lot of different unlearning baselines. And in y-axis, we use this TOW metric to measure the unlearning performance. We first look at this one on the left called retrain. This is the gold standard, as mentioned earlier. And we can see that it achieves maximum TOW by definition because it's a gold standard. And then we look at all the other unlearning baselines. We can see that they all follow the same pattern. If we look at each of them, so from low entanglement to high entanglement, which is from green bars to orange bars to blue bars. their learning performance drops. So, which means a learning problem becomes harder. So here is our first conclusion. If the forget set and retain set are more entangled in the embedding space, the unlearning problem will become harder. And the second factor we found that affects unlearning difficulty is the memorization of the forget set examples. So here for the image classification task, we use Feldman's label memorization definition to calculate the memorization scores for each example. So given an example xi, yi, we use this formula to calculate its memorization score. It is the difference of two terms. So the first term considers the models that train on the entire data set. And the second term considers model trained on the same data set, but excluding this example. So essentially, if an example has a very high memorization score, this means including this example or excluding it during model training can yield very different distributions of predictions on that example. And usually, highly memorized examples are atypical examples or outliers of a data set. So just add a little note here. The memorization score is kind of like a data property for each example of the data set. So now, similar as before, we still create 3 different settings with low memorization examples, medium memorization, and high memorization examples in the forget set. And we still test a bunch of different learning baselines and compare their performance across these 3 settings. And here is the results. So we can see that for most learning baselines here, they still follow a similar pattern. If we look at the low memorization from medium memorization to high memorization, their learning performance drops once again. So here is our second conclusion. If the forget examples are more memorized by the model, then a learning problem will become harder. Now let's take a closer look at these results. So we first look at this one called original, which means we don't do any unlearning here. We just use the original model as the unlearned model. And we can see that for low memorization in green bar, even if we do nothing for unlearning, it can still achieve almost perfect performance, right? And then let's look at these 2 outliers. They kind of behave conversely compared to others. And this is because these 2 are reliably based learning algorithms and usually use over-forgetting for low memorization. And we see that they indeed have lower green bars than others. So, and by over-forgetting here, I mean they cause a larger forget accuracy drop than retraining from scratch. However, this aggressive unlearning strategy actually benefits them for high memorization. We see that for blue bars, they are the best than anyone else. So the lesson we can learn from here is that different unlearning algorithms may be good at different scenarios, and we will use this finding later. So building on these findings, we propose this Refined-Unlearning Meta-algorithm called RUN. It has 2 steps. So in the first step, it's called refinement step. We are given a forget set we want the model to forget, And we partition this forget set into homogeneous subsets with respect to the factors that affects the learning difficulty. And here we use the memorization score as the factor. And the second step, meta-unlearning step. So for each subset of the forget set, we choose the best unlearning algorithm, and then we unlearn each subset sequentially. So we first investigate how useful is the refinement step alone. We follow the similar procedure. The refinement step is the same as previous. We partition the forget set into low memorization subset, medium, and high memorization subset. And the only difference is in the second step. So here we still sequentially unlearn each subset, but we apply the same algorithm rather than choose the best for each. And we want to see how this refinement can improve unlearning. And to distinguish, we call it RUM-F here. And in addition to RUM-F, we also introduce two control experiments called vanilla and shuffle, including the traditional ways to apply an learning algorithm. And we test these 4 SOTA algorithms, and each of them is applied in 3 ways, RUM-F and two control experiments. And we can see that RUM-F is always the best across all the algorithms. So now we can show when we sequentially unlearn homogenized subsets using RUM-F, we can significantly improve unlearning. So then we want to see if we can further improve unlearning by selecting the best algorithm for each subset. So recall our findings previously. We show that different unlearning algorithms are good at different scenarios, right? So now for low memorization, medium memorization, and high memorization, we select the best algorithm for each subset. And we can see it here. And then we follow the procedure in RUM. We first still partition the forget subset into different the forget set into different subsets with different memorization levels. And then we apply nothing to low mem subsets, and then apply fine-tune on medium mem subset, and then saloon on high mem subset. And the result is shown in this gray bar. We can see it is the best among all of them, including the traditional way to apply a learning algorithm, or RUM-F, which means we apply the same algorithm for each subset. And this is when we partially select the best algorithm for each subset. So we can see if we pick the best algorithm for each homogenized subset, we can get further improvements in unlearning. And so far we have shown that RUM can indeed improve unlearning. However, the RUM we used requires prior knowledge of memorization of the entire data set, which can be very expensive to compute. So to make RUM more practical, we introduced this proxy. It is a confidence-based proxy and is much more efficient to compute than memorization scores. So now we still use RUM, but we replace memorization scores with this proxy in the refinement step, and everything else remains the same. And we want to see if using this proxy can still improve unlearning. And the result is shown here. We can see that we can still get similar performance improvements using this proxy, and only with minimal computational cost. So actually, we have a follow-up work on this. The paper is called Scalability of Memorization-Based Machine Unlearning, where we explore several memorization proxies, including this one and some others. And we also study their impact on RAM and their impact on unlearning in general. So I think I'm running out of time, so I'm not gonna expand it here, but feel free to check it out if you are interested. Thank you.